Good morning, students. Welcome back to your physics class. In our previous class, we discussed about excitation energy and the electron potential. We already know what do we mean by excitation energy. So, what is the meaning of excitation energy? The excitation energy is the energy required to take an atom from its lower state to higher state. Means if we are having an electron in n equal to 1 subshell and we have to take it into n equal to 4th of subshell, so we have to provide the energy, and when the electron will jump, the atom will also get excited. So we can say that this energy which we are going to provide is only our excitation energy. After that, we also know that what do we mean by the electron potential. So what is electron potential? The potential through which an electron should be accelerated to gain higher state is called the excitation potential. Means you know what is excitation potential. It is that potential which we have to give to electron, or it is that acceleration which we should give electron so that it can go into its higher state. We have also discussed what was the relationship between the ionization potential and the ionization potential and the energy. So we know that ionization potential is equals to 13.6 multiplied by Z square upon N square volt. So this is our excitation potential. And we also know that what is the value of this ionization potential or excitation potential. So if you are given for calculating it for a helium atom, what you are going to do? So you are going to take for helium, you know that Z will be equal to 2 and the N, the number of orbit, if it is given suppose 1. So cannot we calculate the ionization potential? We can calculate it as 13.6 multiplied by Z value is 2 and its square upon N square, N value is 1, so 1 square, so it is 13.6 multiplied by 4 volt. So this is the ionization potential of the helium atom for its electron in the first subshell. So now let us discuss further about the de Broglie's explanation of Bohr's second postulate. So what do we mean by de Broglie's explanation for Bohr's second postulate? We know that what is the meaning of the angular momentum. So we know that angular momentum was L equals to mvr equals to nh upon 2 pi. So according to de Broglie, when a stationary orbit is the stationary orbit which we talk about is that which contains the integral number of de Broglie waves associated with revolving electrons. The integer could be 1 to infinite, provided it should not be negative. Only this is the value of that integer that we are concerned with. So for the electron revolving in the nth orbit, how can we calculate the radius? Means we know that we have to calculate the radius which is given over here. Means my idea over here will be that how can I calculate the radius which is given over here. So to calculate this radius, what I will do is, first I will put the value of circumference, that is 2 pi r, and its value will be equal to n lambda, and it is also equals to n h upon mv. So here you can see that this is an important relationship which we have got, that is nh upon mv. But here something else also we have got, that is what is the value of lambda. So the value of lambda is h upon mv, and many a times the question has been asked for based on this only, that if lambda is this, then what is the mass of the electron which we have to calculate given that velocity is this, or what is the velocity of electron if the mass is this. So let us do one question so that we can understand for the better. So let's discuss that question. Move to question number 1. What will be the wavelength of the electron revolving in the first orbit of hydrogen atom provided its velocity is 3 meter per second? So given over here that the wavelength of the first of all we will write that what is given to us. So let's see the solution. Given the velocity of the electron is 3 meter per second. Also we know what is the mass of the electron. The mass of the electron is 9.1 multiplied by 10 to the power minus 31 kilogram. So let us solve the question. We know the formula lambda is equals to h upon mv. We have to calculate lambda only, so wavelength will be equal to h. Put the value of h 6.63 multiplied by 10 to the power minus 34 upon mv. So m, what is m? M is 9.1 multiplied by 10 to the power minus 31 multiplied by v. So v is 3 meter per second. So 3 meter per second actually is, this value is very small. So what correction we can do is, we can do that instead of taking this as 3 meter per second, I will take it as 3 into 10 to the power 8 meter per second. Because the electron velocity value is very high, it cannot be so much less. So now let us solve it. So first of all, let us solve the powers. So what are the powers that I get over here? So first of all, I see that minus 31 and minus 34, when solved together we get minus 3, and this 8 goes above and it becomes minus 8. The combined answer of this is minus 11. After that we are remain to solve 6.63 multiply by 10 to the power minus 11 upon 9.1 multiplied by 3. So what will be the value? If we take 6.63 and we divide it with 9.1 multiplied by 3, we get our answer as 2.1. So 2.18 multiplied by 10 to the power minus 11 meter is our answer for wavelength. If we convert it into angstrom, so what we will do is, we will take as angstrom, but for that we have now 2.18 multiplied by 10 to the power minus 1 angstrom. So if we substitute it, we get our answer as 0.2 multiplied by 0.2 angstrom will be our final answer. So 0.2 angstrom is the wavelength that we have for this electron. Now let's move on to the next topic, that is hydrogen spectrum series. What is the meaning of hydrogen spectrum series? So each element emits a spectrum of radiation which is characteristic of the element itself. Means whatever spectrum that it emits, spectrum is actually the due to the electrons we get a spectra, means some lines and their combination, which is due to the excitation of the electron and the energy released by that electron. So that is the characteristic of the element itself, means it is the unique feature of all the elements. So each element emits a spectrum of radiation which is the characteristic of the element itself, full stop. And then we see that the spectrum consists of the set of isolated parallel lines and is called the line spectrum. So we have the parallel lines in the spectrum, and this is called as the line spectrum. Here when we talk about the hydrogen spectrum, this contains approx 5 series which are Lyman, Bamat, Bastion, Bracket and P-Fund. When we talk about the last one, that is the Humphrey Series. So now let us discuss what are these series and what are their uses in our life. So we have discussed what is the meaning of the line spectrum and all. So now let us discuss one by one about every type of series. So first I will take over here as Lyman series. So when I first take as Lyman series, what is the Lyman series? So it is a series of hydrogen spectrum only, but now here the electron jumps from n equal to, means the orbit, the initial orbit can be 2, 3, 4 to infinite, to the first orbit. Now what is the characteristic over here? So characteristic over here is that this n equal to 1 is only for Lyman series, means for any other we cannot have the Lyman series orbit only. The final orbit in which the electron will jump is first orbit in the Lyman series. And what type of region, in which region of light does this lie? So Lyman series lie in the ultraviolet region. So if the question is asked that out of the 5 series, in which of the following series does the Lyman series lie, you will answer that Lyman series will lie in the ultraviolet region. Now when we talk about the next one, we have the Bohr series. When we talk about the Bohr series, what do we have? We have the N2, means from where the electron is coming, can be 3, 4, 5. It cannot be 1. And the N1 in which the electron will be coming will be 2. So this you have to learn that the line spectrum for the Bohr series will be from n equal to 345 to n equal to 2. And here this region will lie in which? So it will lie in the visible region. Means the visible. Next is the Bohr series, which I have talked. It lies in the visible region. In our atmosphere we have the Bohr series. Let's talk about the third one, that is Bastion. So Bastion series is when we have N2 equal to 4, 5 till infinite, N1 in which the electron is jumping is 3 now. The condition is now this will not be equal to 2. And it cannot be equal to n last, means in which the electron will now jump, it cannot be equal to 1 or 2, it will be 3. Therefore we can say that these are specific. Let's take the next example. So after the Bastion series is the bracket series. So when we talk about the bracket series, what do we have? We have the initial orbit of the electron can be equal to 5, 6 till infinite. N1 will be equal to 4. This lie in the infrared region. This also lie in the infrared region. Let's talk about the next one. So the fifth one is the Lyman Bohr bracket Bastion and Fund series. P is silent over here. N2 will be now from 6, 7 till infinite. N1 will be always equals to 5. The region in which it lies is again infrared region. So you should at least know that in the Bastion series also it lies in infrared, in bracket also it lies in infrared, and in fund also it lies in infrared region. The last one is Humphrey series, which is not in our course. So these are the 5 series of hydrogen spectrum, and many questions are formed from this part only. Now let us see what how the hydrogen spectrum series look like. So let us see the diagram. So this is the spectrum of hydrogen. We are going to discuss here the electronic transition for the hydrogen atom. So now let us look at this figure carefully. We see that how many orbits are provided for the hydrogen spectrum. We have for these orbits we have n equal to 1, n equal to 2, n equal to 3, n equal to 4, 5, 6 and 7. So there are total 7 orbitals in the hydrogen atom. Now what are we concerned about? When the electron from any higher level comes into the lower level, it has a spectral series. So let us talk about the first series, that is the Lyman series. So you can see over here that in the Lyman series the electron can either jump from 6, 5, 4, 3, 2 in any of them. When we talk about the Lyman series, from n equal to 2 to n equal to 1 the electron is falling. Similarly from n equal to 3 to n equal to 1 the electron can fall, and similarly from n equal to 4, n equal to 5 and n equal to 6 and also above that. Now when we talk about the Bohr series, the major difference that you can see is that n is equals to 2, means now the electron will no more jump over here, because when it jumps over here, so we can say that now it is considered again when the electron is jumping from any orbit to first orbit, we will always say is as Lyman series only. So now if we have to jump it to the second orbit, now we are telling it as Bohr series. Similarly, when we see about the third one, we see that this Bastion series is from which is n equals to 3, bracket is n equal to 4, and when we talk about the fund, now fund will, all of them will fall over here only. So if I take a different color to show for the fund series, we see that it can fall from here to here, it can fall from here to here. So it will be fund, and the value of fund will be n equal to 5. When you talk about the Humphrey series, so it can fall from above to this n equals to 6 also. So this will be your Humphrey, where your value of n will be equal to 6. So these are your all of the series of the hydrogen spectrum which we have to learn. Also you have to learn that in which of the series what comes. Like if I tell you about over here, we see that in the Lyman series, which type of region we have? Yes, so we have ultraviolet region over here. When we talk about the Bohr series, what do we type of region we have? We have a visible region. When we talk about the Bastion series, I have infrared region. In the bracket series also I have the infrared region, and in the fund series also I have the infrared region. So in all of them I will be having infrared region only, where the electrons are falling and whatever is there, the same series they are emitting. Now let us discuss about the wave model. Now what was the wave model? So till now whatever we have studied, the wave model will always now contradict the above whatever we have studied. So wave model is just opposite of what we have studied. So now let us start studying over here. So in the wave model, we see that the wave model, whole of this is based on the wave mechanics, where the light will behave as a wave. So in that, from there we have took it, and it behaves as now wave mechanics. Now the quantum numbers are the numbers which are required to completely specify the state of electrons. We have 4 type of quantum numbers, that is n, l, m and s. Now what is the meaning of n? N is the principal quantum number. Similarly, when I talk about the L is azimuthal. Then m is the magnetic quantum number, and when I talk about the fourth one, s is the spin quantum number. So these are the 4 type of quantum number which we have over here. The first is the principal quantum number, azimuthal quantum number, magnetic quantum number and the spin quantum number. Now in the presence of strong magnetic field, the 4 quantum numbers we have already seen, which are the principal one. Now when we talk about let us talk about the relationship and the denotation. We know that principal is denoted by n. Now how will we calculate azimuthal? So azimuthal is n minus 1. If the principal quantum number is 4, so the value of azimuthal can be 0, 1, 2, 3, not more than that, because the formula is n minus 1. When we talk about the magnetic quantum number, so for the given value of L, means for given value of the azimuthal quantum number, magnetic quantum numbers can go from minus L to 0 to plus L. Then if we have the spin quantum number are always 2, that can be plus half or minus half, which determines the type of spin. If this is an orbit, here if we have the electron as this and one is this, so this will be plus half. If we denote it as, if another is of opposite spin, we will change its sign. So these are the 4 types of quantum numbers, and which describes the wave model. And with this our atom chapter is over.